Alright, time for another DraftPhysics.com, debatephysics.com also. So you can find those two websites. There is content on them. But anyway, these videos cover most of it. There is a new person I found who fits in the category of a kind of a dissident, I suppose. He has his own theory of how things work, I guess. Don't know the specifics of that yet, except that he's, I guess, a wave ether, whatever. Who knows what the agenda is? There's always an agenda, sadly. They're always incorrect agendas, unfortunately. Todd Grigsby, yeah, Grigsby. I'll quote it again. Grigsby. Yeah, Grigsby. Anyway, so he did a really nice adjustable double slit, sort of in the Brozo style, but even more precise, it would appear. And, sort of draws some very wrong conclusions. And so I'll just go through some of it, in terms of isolating what I consider to be mistakes in what he's saying. And I suppose drawing it will be the important thing to do. So I guess I'll start off with that. Or, I mean, might as well. Yeah. So I guess we'll do this. And we'll probably have to erase the previous slop. Sorry about that. Should have done that ahead of time. It's not erasing very easily. I have to apply extra force, but not extra force squared. All right. All right, so he's made a single slit. All right, that is adjustable, which is nice. I can adjust it in both ways. That means he can move this one or he can move this one. So he can move either side. And what he's attempting to do is see if he creates a piece of pattern, and he's going to take a photo detector, okay, and detect a specific point in the pattern. So he's getting a correct pattern. That is, he's got, a nodes, okay, for the single slit, So there's this double maxima and then your nodes. And so he's basically put it on the third node and is going to, detect how much energy is coming through at that spot, okay, when he does different things to this slit. Now the problem with what he's doing is he really doesn't get that this pattern, okay, varying the slits, you can't really do a single surface and get a fringe pattern. So what he's saying is that when he has a single surface, okay, because he pulled this one back further. So let's say it was here and he pulled it back. He didn't really pull it back far enough is the problem. And he's claiming that the laser beam is just over this surface. And somehow the laser beam is going to make a straight line across the screen. And what he's really done, okay, is that he's made this thing so wide that he's got, maybe 20,000 wavelengths of difference in the distance. It's a huge number. And so they're turning on and off, on and off and off. There's probably thousands of little bars. So he's creating a pattern that has thousands of little bars, and they're all little tiny things, and so you can't see them. It's just the simple truth. So he's not making a solid line. He's making a lot of little tiny bars, and that's all he's really accomplishing. And as he moves it in, okay, he's just making those bars bigger and bigger, and eventually when he gets to a certain closeness, there's only a few wavelengths of difference, and so there's only a few bars that'll show up. But you can't compare these two things, okay, because one of them, this section, is being made out of a lot less light. So what he found is that the brightness goes down by 1/4. So if this has a brightness of 1, when it's a straight line bar, that is when the slits are wide open, it's a brightness of 4 here. Well, that doesn't mean much, because all you're really saying is that when I engage more photons, that is, I put the surfaces closer together. So it's the difference between having a big wide aperture and a small aperture. You can understand that what's the odds of a photon going near the surface? What percentage of the photons go near the surface in this case versus this case? Obviously the percentage goes way up. So you're going to get more light fringes here than you're going to get light fringes here, because so much more light is actually going to go by the surface. And so you're going to be bending, a higher percentage of the photons will get bent because the surfaces are essentially closer to each other. So whatever photons go through are going to have to be close to a surface. And so that's all he's really doing, is saying, yes, you bend more photons, the closer the two surfaces are to each other, more of the photons that go through are going to be bent. That's why there's really an increase. Now, I'd say there's also going to be an increase just because no matter how you do the experiment, there really is energy in these dead spots. Okay, these dead spots aren't really dead. It just means those are photons that are broken still, and so they're not visible. They're out of phase, the pieces, and therefore you don't see a visible photon, but the energy's still hitting. Now, whether or not this detector can detect that subtle difference between broken pieces and non-broken pieces would be an interesting thing to test, but no one's done that, unfortunately. They haven't taken different devices to see if they can take like an infrared images, or the cameras that can do temperature. Be interesting to see, the ones that don't shoot rays at the surface and then bounce them off, but the ones that actually measure the temperature, infrared radiation, whether or not there is the same infrared radiation coming from the dead spots that is coming from the bright spots. That would be an interesting experiment, but we don't have that. So anyway, it's an interesting experiment, but I think he's drawing a wrong conclusion, that if he really did pull the other surface all the way out of the experiment, that is, just eliminate this slit from the experiment, you're not going to get this line anymore, because you do have to have the two sources. You do have to have photons hitting both surfaces to create the fringe pattern. You're not going to create a fringe pattern unless you have the two sources. And it's a fringe pattern. The straight line he's getting is a fringe pattern. So we'll play some of his video just for the sake of, like I said, it's nice that he does these experiments. People interested in physics is always good. Unfortunately, like I said, these people, there's lots of people selling a theory, very few people buying a theory. So so as Franklin Hu would say, there's just no buyers, it's all sellers. And that is the problem we're in. And and everybody gets butthurt if you don't buy their theory. And just a fact. And so the other guy, I don't know what his channel was, Science Debunked or something like that. He deleted his comment, and he doesn't allow comments on his one video. So he obviously isn't much for debating. Okay, he just wants to sell, and he has no interest in defending what he's selling, and that's too bad. Because frankly, if you're not willing to defend what you're selling, you probably shouldn't be selling. That's what I'd say. That's what I do say. That's what I do believe. A little bit ahead.
The single slit experiment.
All right, probably could use a little more volume. So, he's not great at getting this camera stuff exactly great.
Doesn't focus too well, but that's the pattern. I'll leave a photograph. Might be able to stick a photograph in there.
So here,
and there is a
so that's the pattern he got. It's not a bad pattern. It's a pretty good traditional double slit pattern. You can see part of it's blocked out here, but double maxima, and then the dashes go out. Now, as he pulls the other surface away, he doesn't show us this image, but you could see it on the image, is that what's really going to be happening is he's going to have more and more of those little bars, and they're going to get smaller and smaller and smaller and smaller. And so the straight line he's going to create is an illusion. There is no straight line. There's just tiny little bars, and they're so close to each other that you can't see the darks anymore because the brights are overwhelming them. So that's all that really takes place. But you won't see any of that. So let me just jump ahead to where he talks about his device.
So set up that both sides of the single slit can be moved out and in position. So
Now he's got a micrometer on one side, really, really well-made piece of hardware. He went to a lot of trouble. I don't think this is the best use for it. I mean, I think the really best use for it is to really measure how that central maxima, what it exactly does. Does it get a little tiny bit bigger, a little smaller? Does it oscillate in terms of its size?
I'm going to, this is set at 0.5, 0.4 millimeters, and this one's at 0.
All right, so you really don't have to hear all this details. And so we're back here. Somewhere in here is going to be the straight line. I was going to say, look, it's a straight line. It's not really a straight line.
Okay, just a line.
So he just said just a line. And it's really not just a line. It's a lot of pattern.
And that dark spot is, okay, now I take a reading with just a line. And the photosensor's still in the same exact position.
Right. So now the brightness obviously has diminished because you've now separated the two surfaces and very little light is hitting one of them. So now you have less light hitting one of the surfaces, and it needs both to create the pattern. So obviously it's not as bright a fringe. The fringe isn't going nearly as far. And it's creating what he's calling a line, but it's really not a line. It's just the whole pattern that you can see being compressed. The pattern keeps going, so there's millions essentially now. He's got millions of wavelengths of difference between the two surfaces. So now there's a million points where there's a wavelength of difference. The number of wavelengths that fit between the distance is exactly proportional to the number on the surface. It's exactly proportional to half of one side of the surface. Okay. You double it. So there's twice as many as there are wavelengths, because there's really two patterns. One created by the one started with the photons coming from the one surface, one starting with the other one. That's why there's a double maxima, is because the two patterns going this way from these intersections are the only intersections that matter. One of them the two lines, the two vectors are going in the same direction, and then they're both going in the same direction in the opposite way. And that's the important feature, is the direction that both lines are going. And so there's really two patterns, and you've overlapped them. The two surfaces are essentially making a quarter of a pie, and the quarter of a pie is a little spread, and that's why the two are overlapping in the center. And so that would be the real value of this experiment, would be to slowly measure the change in the central maxima and see if it goes a little more than 2, a little less than 2. How big and small does it get? I think that would be very interesting. Oh, wrong mouse.
I moved the left side out, the left edge out. So
the hard part to believe, even by looking at this, is that he's getting anywhere near a 4-to-1 relationship, because it almost looks like there's no light going there now, barely any. But who knows? I mean, with the lights off, maybe it's better.
Take another reading for wattage. Okay. Now I put the left side back in and move the right side out. So I put the left side back in, position at 0.5. Not quite there yet.
So, as stated, so all he's doing is now putting the slits back closer together, reducing the number of wavelengths, and expanding the size of the focal length, you could argue, or something like that, the angular length of the bars. So now the bars are going to get bigger and bigger and bigger because your geometry is changed. You have a smaller triangle base for the lines you're making, and that's why they're getting bigger and bigger, is because it takes more and more distance to be able to create a wavelength of difference. A wavelength of difference takes a bigger and bigger angle change to create a wavelength of difference, because the base of that triangle is getting smaller and smaller. the 2 point sources are getting closer and closer to each other.
So it was 0.4.
All right, jump ahead a little, I think. I don't think there's anything dramatic here. He's just going to do the same thing on the other side now. And
In position. So now I move the right fringe out.
so kind of meaningless in the sense it's just a redundancy. He's going to be doing the same thing again. As he moves it out, the little bars get smaller and smaller and smaller, and you lose the ability to see the on-off pattern, but it's still there, the in-phase and out-of-phase pattern. It's not an interference pattern. It's an in-phase and out-of-phase pattern.
Move the right fringe out. Then going this way. So I'm moving the right fringe out of position.
I mean, you're taking broken pieces and you're putting them back in phase, and then you're putting out of, some of them don't go back in phase, some of them do, some of them don't. 50-50 chance. You're throwing pieces and you're trying to get them to go in the order of AB instead of the order BA, essentially. And there's a 50-50 chance that you'll get, half ABs and half BAs.
Okay, it's way out there. It's way out of the... Okay. Now...
So it's not way out there, because if it was way out, if you actually removed it, you're not going to have a line anymore.
Take another reading. Now this is the right side. This is the left side. The left side is hitting the left blade side now.
So you got them very wide. I mean, they're more than a millimeter apart. But the fact is, there's still laser light hitting that other edge. It's still happening. And you still have 2 point sources. And that's why you have a line. Put the razor blade all the way out, the line disappears.
Okay, so I take another reading, and it should be identical because I haven't moved anything. And this is a very precise setup. And so we get the same pattern. It's supposed to get the same, well, it's not a pattern, it's just a line. So
we know it's not just a line, because if he had a camera on that pattern while he was turning it, he would see that the bars are just getting smaller and smaller and smaller and smaller and smaller and smaller and smaller. And frankly, the further out he puts it, the less and less photons are actually going to be able to do this thing, and eventually the line will disappear. So if he pulls the other razor blade all the way out, there won't be a line anymore.
Measuring the intensity of the line again from the left.
Okay, let's see if he gets a better picture of that. It doesn't look like it gets any better. So he doesn't get the line in that case. The camera doesn't focus on it, and he just cranks it back in again and just does the same thing all over again. And so not much else to say, and so we'll just let him finish up with his statement here about what he thinks all this means.
Okay. Too far.
So he's trying to get the bar size
to
be the same as it was.
1, 2, 3. Now I'm missing it. Anyway, you get it into the third position again. And the left side hasn't been touched this time. So I'm moving it into position. So that, okay, that's about it. Now you're going to be more accurate than what I'm demoing here. Then you take another reading again, and that's your double check. Okay, you can also double check, move the sensor to the left side too. So what happens when you figure out from a single line to the double to the...
So it's not a single line, and like I said, if he did film it while he was cranking it, you would see that it's really a bar pattern that's just getting too small to see.
Interference, the bright fringes increase by 4 times, not by 2. So you got an intensity increase of 4 times.
Yeah, there's going to be a 4-time increase for a lot of reasons. Even when you're randomly throwing things, the idea is that if you have 4 sources, it ends up being that it squares the number of permutations, and so it's a probability math kind of thing. But anyway, it doesn't really matter. I don't think that proves anything. But he claims that proves it's a wave. I don't know.
And that points to wave collisions.
No, it doesn't. Anyway, so yeah, it's not useful in terms of recognizing that all you really did was reduce the number of photons hitting both surfaces by separating the surfaces. The more you separate the surfaces, fewer photons hit the surfaces. Obviously, the light will be less intense that's going to the surface, going to the target. Okay, so that's the video. And he makes other videos just compounding, reiterating this fact, and frankly, doesn't mean much. The better proof against wave theory is the simple radio experiment that shows that photons aren't waving and interfering with each other. So if I have 2 radio sources and an antenna in the middle, I can just move the antenna back and forth in the middle, and I will get the same pattern, because what I'm doing is basically putting them in phase and out of phase, in phase, out of phase, in phase, out of phase. You're just measuring phase, a phase change in the photons. You're not measuring any interference. Obviously, the 2 antenna signals can't interfere with each other in space in that example. All right, so I think that's covers it and such. So this has been draftphysics.com video presentation, and another effort to make simple arguments about that the physics is simple. It's not as complicated as all these people want to make it. It's just momentum, really, in the universe. Things bump into each other, they exchange their energy. Nothing else really happens. So the same energy is always in the universe, and it just changes who owns it at a particular moment. And that's about all that's happening. No gremlins, no pixies, no pole forces, no any of that nonsense.